All right, well, welcome to today's lecture on the classical twin design and biases in the classical twin design when assumptions of the classical twin design are not met. So I'm Matt Keller. I'll be guiding you through this topic today. So buckle up and let's have fun. All right, well, let's talk about assumptions in the classical twin design and biases when they're violated. This sounds like a bit of a downer of a lecture, like something that's negative, but I hope that I can convince you by the end of the lecture that that's not really the case. Biases are inherent parts of modeling in science, and it's important to understand the biases because they allow us to interpret the parameters or the estimates of those parameters that we get from the models correctly and with the proper nuance. So scientific models represent natural phenomena in a logical and simplified way, allowing for better understanding and or prediction of the phenomena under interest. Now, models by necessity must make multiple simplifying assumptions. All models do this, and to the degree that those assumptions are unmet, in other words, that to the degree that the true complexity of the real world is not reflected in the model, which of course it's not going to be, then biases will result to various degrees. This leads to the famous saying from the statistician George Box that all models are wrong, but some are useful. And the point of this lecture is going to be that I'll argue that the CTD, the classical twin design, is useful despite the fact that it's biased. And it's important that we understand those biases to understand how to interpret estimates that come from the classical twin design. The fact that biases exist doesn't in any way invalidate the utility of the model. So because the CTD, the classical twin design, is the most basic and most common design in behavior genetics, it's crucial that you understand the biases in those estimates because it enables you to properly interpret them. So as a generalization, this is a broad generalization, lots of caveats that we'll get to later. The use of the CTD leads to upwardly biased estimates on average of additive genetic variance, which I'll denote here VA, and downwardly biased estimates of dominant genetic variance, which I'll denote VD, and common environmental or shared environmental variance, which I'll denote here VC. Now, the CTD provides decent broad sense heritability estimates, but CTD models typically are pretty poor at differentiating additive genetic variance from dominant genetic variance or non-additive genetic variance, or at estimating shared environmental variance. Now, the extent of the biases from the CTD depend on the quantity that is often unknown, which is how violated those assumptions are. Now, even if unknown, we can guess at what those biases might be or how violated those assumptions might be. Just using logic, or we could try to use alternative designs that don't require the same assumptions as the classical twin design in order to kind of triangulate to estimates that are more accurate or more reflective of the real world. So back to Box, that is George Box, the CTD is undoubtedly a useful tool, but that doesn't imply that its estimates should be taken too literally. We'll talk first about some conventions that we'll use throughout this talk. So we'll denote VA, VC, VD, and VE as population parameters. These are the true values, typically unknowable, that exist in the population. On the other hand, when those same parameters have a hat over them, VA hat, VC hat, VD hat, VE hat, those are estimated values of the parameters. More generally, we can say that theta hat, which is just in general for any of those estimates above, differs from theta, the true population parameter, due to two main sources, right? One is sampling variability, due often to small sample size or to high variation in your variable or your statistic that you're trying to predict, your parameter that you're trying to predict. And the other that we're going to concentrate on this lecture on is bias. We define bias as the expectation of the estimated value minus the parameter in the population. Of course, this is unknowable. So usually we'll have to derive bias by either through simulation or algebraically, which is how we'll do it in this lecture. In this session, we will discuss assumptions of the classical twin design, derive some biases in the CTD estimates when assumptions are violated, and learn how to interpret those in light of those biases. ACE models estimate VA, VC, and VE. Now, it's important to recognize that that implicitly makes the assumption that VD is equal to 0. ADE models, on the other hand, estimate VA, VD, and VE. And again, it's important to recognize that ADE models implicitly assume that VC is equal to 0. Now, there's several other assumptions, in other words, simplifications that all CTDs make, and we'll get to those later and focus for now just on these two assumptions. So here's a path diagram of the classical twin design. This is what's called a direct symmetric representation or way of fitting the model, as opposed to a path coefficients way of fitting the model. The direct symmetric way of fitting is estimating directly the variance components. And I didn't denote those here. I'll just write them down briefly, VD and VA. And same thing over here, VC and VE. MZ twins, we had MZs here, would share the full effects of VC, the full effects of VD, and the full effects of VA, the additive genetic variance. Only the unique environmental effect, VE, would be unshared between MZ twins. DZ twins, on the other hand, let's get rid of that. Can't get rid of it. DZ twins, on the other hand, these are DZs, also share the full shared environmental component, VC, but only a quarter of the dominant genetic variance in the population on average, and only a half of the additive genetic variance in the population on average. So in the ACE model, we're going to fit the ACE model by convention whenever twice the covariance of the DZ twins is greater than the covariance of the MZ twins. 2 times the covariance of DZs is greater than covariance of MZs. This makes some sense because if we tried to fit an ACE model when, say, 2 CVDZ was less than CVMZ, that would necessarily imply that the estimate that we're getting of VC would be negative. So this convention is really there to ensure that none of our variance component estimates go negative, or if you're fitting it with the path coefficient approach, D, A, and so forth, that we don't hit a boundary of 0 on the variance component estimate. The ADE model, by convention, is fit whenever covariance of MZ is greater than 2 times the covariance of DZ. And again, this makes sense because it ensures that none of our variance components, neither A nor D nor E, will go negative. If, on the other hand, we fit this when covariance of MZ was less than twice the covariance of DZ, then our estimate of VD here would go negative. When you're fitting a direct symmetric approach and you notice that one of your variance components is negative, that's a good clue that your model is probably misspecified. Let's first derive algebraic expectations of variance components estimates and the classical twin design. In an ACE model, we assume that VD is equal to 0. So to get algebraic expectations of VA hat and VC hat in an ACE model, The first step is to write down what we assume the covariance of MZs is composed of and what the covariance of DZs is composed of. So assuming that there's no dominant genetic variance, there's a lot of other assumptions that we'll talk about later, but for now, we're really concentrating on just these assumptions. So we're making the assumption that there's no dominance genetics variance, and therefore the covariance of MZ twins is just equal to the VA in the population plus the VC in the population. And by the same tokens, the covariance of DZ twins is composed of half of the additive genetic variance in the population plus the full shared environmental variance in the population. So to get an estimate of one term, so for example, VA, what we need to do is find a contrast of linear transformations of those two equations above that cancel out one parameter, so here, for example, VC, and isolate the other, so for example, VA. So if we want to get an estimate of VA, let's just take covariance of MZ minus the covariance of DZ, all right? Well, that will give us half VA, right? VA plus VC, that's covariance of MZ, minus a half VA minus VC, that's the minus covariance of MZ. I'm sorry, DZ. Therefore, to get a full estimate of the additive genetic variance, we multiply by 2 times the covariance of MZ minus covariance of DC is the additive genetic variance in the population under these assumptions, and therefore an estimator of VA hat is equal to 2 times the difference between covariance of MZ and covariance of DZ twins. Now, similarly, to cancel out VA and isolate VC, we could take 2 times the covariance of DZ twins. That will give us 2 VC, VA, plus 2 VC, and subtract the covariance of MZ twins, minus VA, minus VC, assumed to be equal to the shared environmental variance, and therefore an estimate of the shared environmental variance under the assumption of no dominant genetic variance is twice the covariance of DZs minus the covariance of MZs. Now, I should have warned you that this talk requires audience participation. And so while I cannot be in your room and make sure that you're doing this, I highly recommend that when we do these pen and paper practicals throughout this lecture, that you stop the video and try to work out the questions first, and then come back to the video and start it up again and see how you did. So using what we just learned to derive algebraic expectations of the estimates of VA and VC, well, what we just learned to get the estimates of VA and VC in an ACE model, what I'd like you to do is get the algebraic expectations for estimates of VA and VD in an ADE model, where we assume that the shared environmental variance is 0. So as a hint, in this situation, we're going to assume that VC is 0, and therefore that the covariance of MZ twins is equal to VA plus VD, and that the covariance of DZ twins is equal to a half VA plus a quarter VD, again, assuming VC is 0. So to get VA hat, think of possible contrasts of linear transformations of these two equations that cancel out VD and isolate VA, and vice versa for VD. So the first question I'd like you to work on, what is your estimator of VA hat in an ADE model? And what is your estimator of VD hat in an ADE model? So pause the video and come back once you think you have your answers. We'll see how you did. All right, well, let's go through this. So again, the covariance of MZs is assumed to be equal to VA plus VD. Covariance of DZs is assumed to be equal to a half VA plus a quarter of VD. We want to get an estimator of VA. So we want to cancel out VD and get an estimator of VA. Well, let's think about this. One way we could try to do this is take 4 times the covariance of DZs. That would give us 4 covariance DZ minus the covariance of MZ. Let's try see what happens if we try that. 4 times the covariance of DZ would be 2 VA plus VD, and then minus VA minus VD would be VA. Therefore, an estimator of VA hat is 4 times the covariance of DZ twins minus the covariance of MZ twins. These are estimates. All right, now how do we go about getting an estimator of VD in an ADE model? Well, if we take, say, covariance of MZ minus covariance of DZ, well, that's going to give us, well, that will give us a half VD plus VA. Well, that's not going to work. So if we did this, right, we would have VA plus VD minus a half VA minus a quarter VD. So this would give us a half VA plus 3/4 VD. So that's not very helpful. Let's erase that and try again. What if, on the other hand, we took covariance of MZ minus twice the covariance of DZ? This would give us VA plus VD minus VA minus a half VD. Now, I think we're in business because these VAs cancel out and we're left with a half VD. So therefore, 2 times the covariance of MZ minus twice the covariance of DZ would be an estimator of VD, or rewritten 2 times the covariance of MZ minus 4 times the covariance of DZ would be an estimator of VD. Let's talk now about how to get algebraic expectations of the bias in estimates that's due to misspecification. In other words, due to a violation of an assumption that we had to make to fit our model. So we want to know what happens when we must misspecify the model. Here, when a parameter assumed to be 0 in the model isn't 0. So to do that, first write out one of your estimators. So for example, in the ACE model, with an estimator of VA is 2 times the covariance MZ minus covariance DZ. Now consider the true composition of parameters used in the estimators. So in other words, if you get an assumption wrong. So if VD is actually non-zero, then the true composition of covariance MZ is equal to VA plus VC plus VD. And the true composition of covariance DZ is equal to half VA plus VC plus a quarter VD. And then finally, we just substitute the true compositions of covariance MZ and covariance DZ into our estimated covariance DZ, estimate covariance DZ used in the estimator. And therefore, for an estimator of VA in the ACE model, we would have 2 times the composition, the true composition of MZs if we didn't get the assumption correct, which is VA plus VD plus VC, minus the covariance of DZs, which is, if we got the assumption wrong, a half VA, quarter VD, and VC. And if you do that, what you'll see is that your estimator of VA is actually made up of VA, which is good, plus 3 halves of whatever VD is. So in words, whenever VD is 0, but one fits an ACE model, VA hat is biased upwards by 1.5 of whatever VD truly is. Welcome to our second pen and paper practice, deriving biases of ADE models. So usually we just learned in the ACE model to derive the bias of VA and VD hat in the ADE model, where we are assuming VC is equal to 0. Recall that the additive genetic variance estimator that we got is for CVDZ minus CVMZ, and the estimator that we got for VD hat is this. And these are the true compositions of the covariance MZ and covariance DZ if we got the assumption that VC is 0 incorrect. All you need to do here is just substitute the true composition of those covariances into the estimator and see how our estimates are biased. So get an estimate of VA hat, then get an estimate of VD hat. Pause the video, do this pen and paper, and see you back in just a sec. All right, let's see how you did. So we know what the covariances of MZ and DZ are made up of. I won't write that down again. I will write down what our estimator of VA hat is. This should be 4 covariance DZ minus covariance of MZ. We substitute in the true compositions of these rather than the estimates. We would get 4 times a half VA plus a quarter VD plus VC minus VA minus VD minus VC. This would give us 2 VA plus VD plus 4 VC minus VA minus VD minus VC. So we get rid of the VD. We indeed get VA as being a component of our VA estimator, which is good. But plus 3 VC. So the estimate of VA in an ADE model is equal to the true VA plus 3 times whatever the VC is in the population. So VA hat in an ADE model is upwardly biased by 3 times whatever VC hat or whatever VC is in the population. Now, of course, VC itself can't be too high, or else we would have been fitting an ACE model, because twice the covariance of DZ twins would have been greater than the covariance of MZ twins if VC gets too great. So it's not like anything is possible, and it's not like this bias is necessarily that large when you're fitting an ADE model, but it still needs to be kept in mind that the estimate that you're getting of VA hat could well be overestimated if shared environmental variance actually exists. What about VD hat? So VD hat, their estimator there is 2 covariance of MZ minus 4 covariance of DZ. We just put in what we have up here. So this would be 2 VA plus 2 VD plus 2 VC minus 2 VA minus VD minus 4 VC. The VAs cancel out. The VDs give us a VD in our estimator of VD hat, which is good. But now we are being underestimated by 2 times whatever VC is. So in words, the estimate of VD from an ADE model can be underestimated by twice of whatever the shared environmental variance is. Let's go through some quiz questions, and whenever I do this at the end, just pause the video and then I'll give a little pause and then start it back up and see how you did. Quiz question 1, we must fix to 0 either VC hat or VD hat in an identified CTD model because, and then choose all that are correct. I'll let you look through those and pause the video and be back in a sec. Okay, welcome back. So why must we fix to 0 either VC or VD? Well, it isn't because of multicollinearity. It's not because VA and hat and VC hat and VD hat are too correlated. In fact, you could think of them as being perfectly correlated if you're trying to fit all 3 together. So this isn't correct. And B, you can estimate VC hat and VD hat simultaneously. You just have to fix VA hat to some specific value. In other words, or for example, 0. This is actually correct. This is one of the correct answers here. So we've talked here about ACE models and ADE models. You could also fit, if you chose, a CDE model by fixing VA to whatever value you wanted. It could be fixed to 0, which is kind of by convention the way we're doing the other parameters. It could also be fixed to 0.05 or to 0.1, whatever you want. And if we do fix VA, we could fit a model with both C, VC, and VD in it. And that would be an identified model. I'm not saying that that model makes good sense. For the same reason, it doesn't make good sense to retain a interaction in a model, but drop the additive term or terms. Dominance is a type of within locus interaction, and it's likely that even if there is a true biological interaction within a locus, in other words, there's a true dominance effect in a locus, it's very likely that a lot or even most, and actually in some situations, almost all of the variance due to that dominance effect is actually additive genetic variance. For the same reason that in an interaction, unless you just so happen to have a perfect crossover that's perfectly balanced in all 4 of the cells, that an interaction effect has some kind of additive effect associated with it. And often that additive effect is larger than the variance accounted for by the interaction. I should note here in the ADE model, we could have fit, by convention, we're fitting VC as 0, but we could have fit VC to equal 0.05 or 0.10 or whatever we wanted, and then still fit an ADE model that would have been identified. And by the same token, with an ACE model, we could have fit VD to be 0.05 or 0.10 or whatever we wanted to fit, whatever we wanted to assume. And the ACE model would have still been identified. Okay. C, you can estimate BC hat and VD hat simultaneously. You just have to allow them to go negative. In other words, not use the path coefficient approach, where we have a path coefficient that we're trying to estimate, but we fix the variances to 1. But we should have instead used a symmetric direct approach where the path is fixed to 1 and the variance is what we're estimating. That's called a direct symmetric approach. That is not correct. The direct symmetric approach is important for several reasons. Most prominently, it gives us the correct type 1 and type 2 error rates. Well, it gives us the correct type 1 error rates, and it doesn't inflate our type 2 error rates if we use that approach. And this is discussed in a paper by Verholst in 2019. But that approach does nothing to the issues that we're discussing here with respect to parameter indeterminacy and trying to fit 3 parameters, VC, VA, VD, all having to do with in-family similarity, but with only two informative statistics, covariance MZ and covariance DZ. So I guess I gave away the final answer that is correct, and that's D. So why can't we estimate VC hat and VD hat at the same time using twins only? Well, solve these 2 following equations for VA hat and VC hat and VD hat. You can pause the video if you want to try, and I'll wait here for you. Or you can just recognize that, hey, this is impossible. There's 2 informative statistics that we're going to try to use, covariance MZ and covariance DZ, but there are 3 unknowns we're trying to solve for. You cannot do that. Can't be done. There are no unique solutions. There's actually an infinite number of possible solutions to this, these 2 equations, and therefore the model is unidentified. Now here, that non-identification is obvious, but sometimes non-identification is challenging to see. Now you can empirically detect non-identification by noting that A, the model estimates depend on the starting values. So you change the starting values in maximum likelihood, whatever you're using, OpenMX hopefully, and you get different estimates depending on your start values. And B, that the final model, each of the final models that you fit, each of them having different start values and different most likely estimates, have identical -2 log likelihoods. If that happens, you have identical likelihoods, and that the final estimates depend on the start values, that is a symptom of non-identification. That's called checking non-identification empirically. And it's useful to do that when you have models where it's not obvious how or why it is or isn't identified. And finally, you could use OpenMX and use this function called MX check identification to see if your model is identified. Now, just because we cannot fit VC hat and VD hat simultaneously in the CTD does not mean that one or the other's true value is 0. I mean, this is one of the main points of this whole lecture. However, when we try to fit an ADCE model with just twins, there's an infinite number of combinations of VA hat, VC hat, and VD hat that fit the data equally well. This is called parameter indeterminacy and is a necessary consequence of model non-identification. You can think of this visually, this issue of parameter indeterminacy and non-identification. If you think about a likelihood surface, and we're trying to maximize a likelihood surface, in an identified model, the set of parameters that maximize a likelihood are at the top of a likelihood hill. That would be in 3 dimensions, 2 dimensions, and 1 being the likelihood. But here, obviously, we've got more than just 2 dimensions. We've got 3 dimensions. We're fitting an A, well, 4 dimensions, an A, a D, a C, and an E parameter. So it's hard to think in 5 dimensions because we have 4 dimensions of parameters and then a maximum likelihood dimension. But if we just think in just 3 dimensions, then the most likely estimates would be at the top of that hill. And there would just be a single set of parameters that would maximize the likelihood. That's if you have an identified model. If you don't have an identified model, on the other hand, the way you could visualize that likelihood surface is that it would rise up and then it would hit a plateau that's perfectly flat. And there are an infinite number of sets of estimates on top of that plateau that are each equally likely to one another. Right, so that's how to visualize parameter indeterminacy. When we have parameter indeterminacy, we just have to fit either in the classical twin design, either an ADE, assuming that VC is 0, or an ACE, assuming that VD is 0, and live with the potentially biased estimates. But it's good to quantify that bias and interpreting those estimates. So quiz question 2. If the assumptions of the CTD model that either VC or VD is 0 is violated, in other words, if A, C, and D simultaneously influence the phenotypic variation, then, and choose all that apply. I'll let you pause the video, come back in just a sec. All right, welcome back. So A, the interpretation of the estimated parameters should be altered. In other words, out of the genetic variance should be considered an amalgam of VA and VD in an ACE model, or of VA and VC in an ADE model. Well, this is correct, right? What about B? There's no point in doing the analysis at all. Wrong. All models are wrong. Some models are useful. The estimated parameter values will be biased. That also is true. Don't think we need to discuss this much further. Quiz question 3, in an ADE model, we find that VA has 0.3, VD hat is 0.1. This implies that shared environmental factors do not influence the trait in question. Let's pause the video. Okay, welcome back. This is clearly false, right? It's the point of this lecture, really, is that just because we're making an assumption doesn't mean that the assumption is true. This question 4, we run an ADE model and find that VA hat is 0.69, the VD hat is 0.05. Now, if in truth VC is 0.1, now of course in real life we're never going to know what a population parameter actually is, but we could know in simulation, and we could know, if you happen to be a really good friend of a deity and they come down and they say, by the way, VC is actually 0.1. Then you would know what VC is, and you'd know that you have a bias. If you have a bias estimate. Now, if on the other hand, the deity comes down and says, by the way, VC is actually 0.0000, then you would know that your estimates aren't biased, at least not biased due to this issue of parameter indeterminacy. Now, if in truth VC is 0.1, what will the effects on the estimated parameters be? I'll let you look through this and then pause the video and come back. Okay, welcome back. The answers that are correct are B, VA will be biased to be too high, and C, the estimate of VD will be biased to be too low. You can see algebraically from what we've done by deriving the estimates of the bias to figure out what the true VA is by just plugging in the numbers. We know that the estimate of VA is equal to the true VA plus 3 times whatever the shared environmental variance is. And if we got an estimate of 0.69, and we know, because we're good friends with the deity, that the true shared environmental variance is 0.1, this implies that the true additive genetic variance is 0.39. So we got an estimate of the additive genetic variance of 0.69, but because we violated the assumption that VC is 0, the true additive genetic variance, which we would not have known, is 0.39. You can do the same thing with the estimate of VD. This is equal to VD minus 2 VC. And here we had an estimate of 0.05. This would lead to the true VD being equal to 0.25. So we estimated VD hat to be 0.05. We estimated VD to be 0.05, but the true VD in the population was actually 0.25 because we got that assumption about VC being 0 incorrect. So here is a rundown of what we've kind of gone over in this talk. In ACE models, where the bias induced by setting VD to be 0, the VA hat is going to be equal to the true VA plus 3/2 of whatever VD is. The VC hat is going to be equal to VC minus half of whatever VD is. In an ADE model, the VA hat will be VA plus 3 times whatever VC is. And in an ADE model, VD will be VD, the estimate of VD will be VD minus twice whatever VC is. Thus, VA is typically overestimated and VC and VD typically underestimated in the classical twin design. Now, the degree of that over or underestimation depends completely on how violated these assumptions are. If the assumptions are not very violated, then the bias that you get will be not very large. If they're biased a great deal, then they're obviously going to be, if the assumption is violated a great deal, the bias would be quite large. But this is only talking about the biases due to this issue of not being able to fit 3 variance components that we think might be very important for causing within family similarity, shared environmental effects, as well as 2 types of genetic effects. But things are more complicated when you consider the possibility that there's other types of genetic effects. For example, there's other types of non-additive genetic effects, such as additive by additive epistasis, or 3-way epistasis, or 4-way epistasis. And also assortative baiting and gene environment correlation, gene environment interaction. All of these other issues are phenomena that we have to make assumptions about in the classical twin design. And for the most part, we're assuming that none of those things actually exist. And if they do exist, and they're important, we're going to get biases due to those factors too. And I'll talk a bit about that in a sec. What I do want to talk about briefly is just the effect of epistasis on these biases. So epistasis refers to between locus interactions, as opposed to dominance, which refers to within locus interactions. And epistasis can increase the degree of biases because it can reduce the covariance DZ to covariance MZ ratio that's due to non-additivity even further than the expected 1:4 ratio that we model under dominance. Now, the degree of that bias rests on how strong the higher level epistatic influences are. And that's an active level, that's an active area of debate. Epistatic effects will generally come out as being estimated in VD hat. Therefore, interpret VD hat broadly as a rough estimate of V in A, variance due to non-additive genetic effects, which you can think of as being a weighted amalgam of all the different types of epistatic effects that exist. So additive by additive epistasis, additive by dominance epistasis, dominance by dominance epistasis, additive by additive by additive epistasis, so forth and so on and so on. My take, and this is not just mine, this is something that most quantitative geneticists probably agree with, is that the additive genetic variance is almost certainly greater than the non-additive genetic variance. And that's true for the same reason that statistical interactions in linear models, that when there is a statistical interaction, we expect the variation explained by the interaction between two or more variables will almost certainly come out or bleed out into the lower order terms. So for example, the variables involved in a two-way interaction will still have an average effect across the levels of the variable, and under most scenarios, the variation due to the additive effect will typically be larger than the variation due to the interaction. And similarly, in most situations, three-way interactions will lead to greater variation due to the additive effect than the two-way effect, which in turn are going to be larger than the variation due to the three-way effect. And that's just simply because as I said actually before, if you've got an interaction, it's very unlikely that a two-way interaction in this case, that it's going to be a perfect crossover with cells just the right size, such that all of the variation comes out in the interaction and there's no additive effect. In fact, most interactions, like say this type of interaction, you're still going to have some kind of additive effect. And often that additive effect is larger. The variance explained by that additive effect is larger than the variance explained by the interaction. And for that same reason, we expect that the variance explained by additive genetic effects is going to tend to be larger than the variance explained by interaction effects such as dominance or epistasis. And therefore, most quantitative geneticists are skeptical that a large amount of variation is due to higher level epistasis. Quiz question 5, what are the typical assumptions of a classical twin model? Pause the video, come back in a sec, we'll go over it. Okay, welcome back. So the correct answer here, so only genetic factors cause MZ twins to be more correlated than DZ twins, correct. Either VD or VC is 0. This is what the lecture has been about, correct. There is no epistasis. We're modeling all non-additive genetic variation as though it's due to dominance, correct. That there is no assortative mating, correct. And finally, that there is no gene-environment interaction or correlation, also correct. So here I go over what the effects of those violations of assumptions would be if they are teeth violated. So A, only genetic factors cause MZ twins to be more correlated than DZ twins. If that is violated, then our estimates of genetic factors are going to tend to be overestimated, and our estimates of shared environmental factors will tend to be underestimated. This is actually the most important assumption that we make in a classical twin design, more important than this issue of parameter indeterminacy between the A, D, and C parameters. It's kind of an all bets off if this is wrong. And this has been looked at empirically in several cases and been shown to probably not be a very large violation, but just because it's not large doesn't mean it's never violated or not violated to some extent. So it is something that we need as behavioral geneticists to keep in mind whenever we're getting estimates from twin designs. Second, either VD or VC is 0. This is what we've gone over ad nauseum in this talk. 3, no epistasis. If that is violated, then VD hat or VA hat will be overestimated, and the shared environmental variance will be underestimated. Assortative mating, on the other hand, will lead to the opposite bias. If there is assortment in the population, in other words, if mates are more like each other than expected by chance, and if those traits are heritable, then this will lead to VA and VD being underestimated and VC, the shared environmental variance, being overestimated. And we'll talk about that a bit more in the companion lecture to this where I go over extended twin family designs. And finally, no gene environment interactions or correlations. If we're talking about an A by shared environment interaction, that will tend to lead to the additive genetic variance being overestimated. If we're talking about an A by unique environment interaction, that will tend to lead to the E being overestimated. And if we're talking about a passive covariance AC, also called genetic nurture in the literature, that will lead to VC being overestimated. So in conclusion, all models require assumptions. Generally, the more these assumptions are violated, the more the estimates you get from the model will be biased. Understanding these biases allows us to understand how to interpret those estimates that we get from those models with the proper nuance. In all models, including in the CTD, be cautious of reifying parameter estimates. VA hat is not a pure estimate of VA for many, many reasons. We really focused on one of those reasons, having to do with not being able to fit everything we want at the same time. Not being able to estimate VA, VC, and VD simultaneously. But that's just but one reason that VA can be under or overestimated. And it's important to have those factors in mind when you're interpreting the estimates. VA hat should be interpreted as an amalgam of mostly VA, but also VD and VC. And here I'm really just concentrating on this issue of VA, VD, and VC not being able to be estimated simultaneously. The estimates of VC and VD may often be underestimated. We should interpret VD not as a true or pure estimate of dominance variance per se, but rather as an estimate of the non-additive genetic variance more broadly. And finally, the estimates of heritability in an ACE model or an ADE model, and here I mean the broad sense heritability, are probably pretty good estimates of that same quantity in the population. So with that, I will bid you adieu and hopefully see you in our next lecture on extended twin family designs. Thank you.